Alright, this example starts on page 6-17 of the course pack. For the following stress state, draw the Mohr circle, find the principal stresses, find the maximum shear stress, and find factors of safety using maximum shear and maximum distortion energy. This is Tresca. This is von Mises. The yield strength of the material is 36,000 psi. So our step one is drawing Mohr's circle. We start that with axes. We know that our sigma x is negative, so we should probably skew our axes with the origin to the right. Sigma y is 0. So our first step is to plot our first point, which is sigma x, comma, tau xy. And remember, this is our sigma, and our shear is positive down, so that point is minus 8,000, comma 3,000, and minus 8,000 plus 3,000. We'll call that roughly there. We plot our second point, which is sigma y, and the negative shear. So that is 0 and minus 3,000, and we'll call that approximately here. The next thing that we do is connect our 2 points with a line. We know that the location of that intersection with the sigma axis is our average stress value, sigma x plus sigma y divided by 2. So minus 8,000 plus 0 over 2 ends up being minus 4,000 is the location of the average stress. Then we need to know the length of the radius of the circle. That is difference squared plus the shear squared, the square root of that. And that actually ends up being a 3, 4, 5 triangle. So that's 5,000 psi. So now defining the circle that goes through our points. Or approximately through our points. We know that sigma A is the average stress value plus the radius, so that's minus 4,000 plus 5,000. Sigma A equals a plus 1,000 psi, and we know that the location of B is the average minus the radius, or minus 4,000 minus 5,000. So the second principal stress is down here at minus 9,000. Now, we have to remember that in a state of plane stress, our sigma C is always hanging out there at the origin. Then we need our maximum shear stress. So reorder sigma A, B, and sigma C to sigma 1 is the largest one, is plus 1,000. Sigma 2 is stuck in the middle as 0. Sigma 3 is our minus 9,000. And then we know that our max shear is then So, after one more Microsoft Word crash recovery, we had drawn Moore's circle. We figured out that the principal stress is sigma A, 1,000, sigma B, minus 9,000, sigma C equals 0. So we reorder these by magnitude, and we get sigma 1 is 1,000, sigma 2 is 0, sigma 3 is 9,000. And from that, we use the fact that our maximum shear stress value is always sigma 1 minus sigma 3 over 2. So our max shear is 1,000 minus a minus 9,000 over 2, otherwise known as 5,000 psi. Now, looking at failure criteria, what did we want? We wanted factor of safety using maximum shear. So max shear stress criteria is that our factor of safety in is the yield strength of the stuff over 2 times the maximum shear in the material. Our yield strength, tensile yield strength, S sub capital Y, is 36,000. We just figured out that our max shear is 5,000, so 2 times 5,000. That ends up being 36,000 divided by 10,000, or 3.6. Alright, now for our maximum distortion energy, also known as von Mises, we need our von Mises equivalent stress. That is our sigma prime, and you can get that in two different ways. We can say sigma prime equals sigma A squared plus sigma B squared minus the product of the two. Or you can use the values from the arbitrary stress state, sigma x prime squared, sigma x squared plus sigma y squared minus a product term plus 3 times the shear squared. Okay, in this case, sigma y is 0, so that term goes away, that term goes away, and this would simplify over here to minus 8,000 squared plus 3 times the shear stress, which was 3,000 squared. So sigma prime, doing the math, ends up 9539 psi. If we come back on this side and use our sigma A and sigma B, sigma A being 1,000, so 1,000 squared, sigma B is minus 9,000, and then minus the cross term, 1,000 minus and that is a product in there, 1,000 minus positive 1,000 times minus 9,000. And doing the math, you end up with the same number, either way. So our factor of safety N for the von Mises equivalent, or for the von Mises criteria, distortion energy criteria, is the yield strength of the material over that von Mises equivalent stress, 36,000 over 9539, 3.77. So fairly close, 3.6 for the shear stress criteria, 3.77 for the distortion energy, otherwise known as von Mises.